The implicit function theorem does extend really nicely to functions of 3 variables as well. So the way this works when you have 3 variables is let z be a function that is implicitly defined in terms of x and y. Sticking with what we did in the previous video, we'll go ahead and say that a function of x, y, and z is equal to 0. We're also going to assume that z is actually a function of x and y. So f is a function of 3 variables, x, y, and z is a function of 2 variables, x and y. Now we're going to come up with 2 different ways that we can calculate the partial derivative of z with respect to x and y. The first method is going to be, let's go ahead and take the partial derivative of both sides of the previous equation with respect to x. Now on the left-hand side, we'll need to make use of the chain rule, and there are 2 ways to get from f to x. Those 2 ways would be to go straight from f to x along this branch, or we can go from f to z and from z to x. If we perform the same algebra as what we had done previously, we can solve for the partial derivative of z with respect to x. This would be the negative partial derivative of f with respect to x divided by the partial derivative of f with respect to z. This is another form of the implicit function theorem and is really handy anytime you're dealing with things that are not functions in 3 variables. For example, quadric surfaces are a great thing that this can be used for. Additionally, we can come up with another one by saying, let's differentiate with respect to y. So if we took our original statement, our implicitly defined function back up here, and differentiated with respect to y. Going back to our tree diagram, there are 2 different ways to get from f to y. We can go there directly, partial derivative of f with respect to y, or we can go from f to z, then z to y. So f to z and z to y. Performing the same steps of algebra to solve for the partial derivative of z with respect to y, we will get the following. First, we subtract the partial derivative of f with respect to y, and then we divide by the partial derivative of f with respect to z. So it's looking like we're starting to see a nice consistent pattern when it comes to these partial derivatives. There will be a negative, and given that there is a negative, we're also going to flip the locations of the z and the y. So y goes up top, z goes in the bottom, or x goes up top, z goes in the bottom. Now, the longer explanation for why that works is in order for something to be in a denominator, it's going to be in the denominator of the numerator. Whereas this z is up top, and the reason that it's up top is because that z is actually in the denominator of the denominator. So that's sort of the mindset to get into as far as why these 2 variables look like they're flipped.